Look at electronegativity. We've looked at the bonds with respect to length and strength. We'll look at strength again later. But we're going to look at electronegativity. Now, when we have our bonds, we have three different types of bonds. When electrons are shared equally between two atoms in a bond, then we have what is called a pure covalent bond. That means that they're shared evenly, they spend equal time, etc. Now, the electrons can be shared unequally in a bond. And when you look at it, if you're looking at them as electron clouds, then the one that the electrons spend more time with is the bigger cloud. And these are called a polar covalent bond. It's still a covalent bond. The electrons are shared, but they're not shared evenly. Now, remember, if electrons are transferred, they're going to form ions, which means you have an ionic bond. So what you're looking at here is going from even sharing to totally transferred. So what we're trying to show you is that you're on a spectrum from you totally shared to you totally transferred, and there is gray area in between. All right, so how do we get to this gray area? Well, the reason why the electrons are not shared is something called electronegativity, which is the ability of an atom in a molecule. You can't have an isolated atom. This is an atom in a molecule attracting electrons to itself. Now, Linus Pauling was an American scientist who got a Nobel Prize for this, and he set the scale with fluorine as the highest. So basically what the general trends are, it's going to increase left to right across the periodic table, and it's going to decrease down a family. And I hate increasing and decreasing. So basically, we're going to increase here. The biggest bully on the block, and we're ignoring the noble gases, is fluorine. All right? Now, we ignore the noble gases because the noble gases aren't going to bond. Look, you can make them bond, but they're not going to bond in general. So that's your trend. Basically, the biggest thing to remember is the biggest bully on the block is fluorine. Then it's oxygen, then it's nitrogen and chlorine, then it's the other halides and sulfur, and it goes down from there. So if you can remember this little chart here, life is good, especially when you go into biology, because you don't encounter much fluorine in people. Fluorine's kind of bad. Okay, except in teeth, because you find fluoride in your toothpaste. But oxygen and nitrogen are your biggest components that make polar bonds in organic compounds. So the way I describe electronegativity is if you have a 5-year-old and a 10-year-old and you have one handheld game, and you give them the game to share, which person is it going to spend? And let's assume they both like the game. Don't take that out of the equation. But if they both like the game, then it's really going to spend more time with the 10-year-old than the 5-year-old typically, because the 10-year-old's bigger. So might makes right in his case. So electronegativity works the same way. The more electronegative the element, the more it's going to want to take over the electrons. Now, here's the chart out of your text, which confuses me because I don't like this 3D stuff. It may work for you, and if so, that's great. So this, remember, is increasing electronegativity. And here are your 3 highest ones. Notice that it drops off as it goes down. And hydrogen actually kind of comes over here on top of carbon, and it makes it work. Now, do you need to know these values? No. You just need to know the trends, and you'll be good to go on that. All right, so when we look at the effect of electronegativity, what do we get? Well, because the electrons spend more time on one atom in a bond than the other, we end up with partial charges associated with what we call a polar molecule. And a polar molecule indicates, or a partial charge indicates, that the electron distribution within the bond or the molecule is uneven. Okay, and there are a couple ways we can designate it. The easiest way is to designate it with a sigma or a delta symbol. Excuse me. This is the Greek delta, and that one kind of doesn't look good. It's like a figure 8, except you don't finish it. So there's your delta. You can have a positive or a negative on the delta. So if we were looking at HCl, we know that chlorine is more electronegative, so that the H plus will have a partial positive and the chlorine minus will have a partial negative. Now, another way to indicate this is this symbol right here, which works actually better for a lot of people, because what this does is it says that the electrons are being pulled towards the chlorine, which leaves a partial positive on the hydrogen. So as we said before, we get a partial negative, partial positive, okay? If you look at the magnitude of the polarity difference, this involves not only the electronegativity, but the distance between the partial positives and the partial negatives. You actually measure this by a dipole moment. And a dipole moment has the symbol mu, which is in debye's, which is really a difference in electronegativity within a molecule. So again, we look at the charge distribution, the distance, and we get that combined in a debye. So basically what it boils down to is the more polar a molecule, the higher its dipole moment is. So if you look at an electron distribution map of species in the same family, we have HF, chlorine, bromine, and iodine. Remember, fluorine is the most electronegative, and it drops off, so iodide would be the least electronegative. And notice that you have a full positive, full negative, more red. So you get this whole full red thing going here. Here you start getting a little less red, and it keeps decreasing as you go. Now notice you still have an uneven distribution because of the size issues, but you don't have an uneven distribution per se of the electrons, okay? So remember, X is a generic symbol for the halides. So if we continue looking at this, so what do we do with electronegativity? Well, what that allows us to do is determine the bond character. And the bond character has 3 states. We have pure covalent, which means we're evenly shared. We have polar covalent, which means we're sharing, but we're not sharing evenly. And then if we do a full transfer, we have an ionic bond. So if you look here, for an ionic bond, you basically have total red, which is negative, and total blue. If it's a polar covalent, you still have the red and the blue, but it's not as extreme. And if you have a pure covalent, then notice it's an even sharing. So the difference is in the difference in electronegativity. So if you're less than 0.5, you'll be pure covalent. If you're between 0.5 and 2, you're going to be polar covalent. If you're greater than 2 or greater, you're an ionic bond. Now, one thing I'm going to point out to you several times, all hydrogen-carbon bonds are pure covalent. Now, the reason I point that out is occasionally you'll actually have it sit at 0.5, which would make it a polar covalent. depending upon where you get your electronegativity. But in the case of carbon and hydrogen, they are they are not a polar covalent bond. They are a pure covalent bond. Now, your polar covalent tend to have your usual suspects, fluorine, oxygen, nitrogen, chlorine, and the halides as you go down. And remember, ionic bonds are metals and nonmetals, because the farther you get from each other on the periodic table, the more ionic you're going to tend to be. So sometimes, if when in doubt, if they're very far apart on the periodic table, unless they're both metals, then they are going to be ionic. So you're good to go there. Let's work a problem. So if we look at identifying the partial charges, and you're asked to use the delta symbol here. Remember, this is your electronegative. Again, I'm going to point this out. Nitrogen, chlorine, the halide, sulfur. Whoops. Let's do that as common sulfur, and it drops down. So the most electronegative species will get a negative. The hydrogen will get the positive, because remember, the electrons are being pulled this way. Nitrogen here is the most electronegative, so it gets the negative. Boron would get the positive. So notice in the first case, the electronegative species was written last. In the second case, it was written first. Does it matter? No. We can put it anywhere we want. We should just always know that the most electronegative species is negative. So here we have carbon and we have chlorine. So carbon is going to be less than electronegative. Finish the little symbol. So it's going to be positive. Chlorine's negative. So when we start to compare bonds here, and we're comparing HCl, HS, and HF, we're asked to put them in order of increasing polarity. Remember, increasing and decreasing are important. So if we're increasing, we're going to have the lowest to the highest. So when we look at this, the hydrogen is the same, so all we're really looking at is the electronegativity of our other species. This is the highest. Sulfur would be the lowest, with chlorine in the middle, if you look at your little chart over here. So the lowest would be HS. It's going to be less than HCl, is going to be less than HF. So that one was easy. So now we look at this set down here in B, and it's like none of these elements are the same. So wait a minute. When you look at them, sometimes one of them will kick out. This one should, because we said that this one's pure covalent. So that means that it is nonpolar. We'll get to that again, but that means it's nonpolar. So if we look at the periodic table, and your periodic table is your best friend, so we know that phosphorus on your periodic table sits here, and sulfur sits here, and oxygen is going to sit here, and silicon is way over here. So if you notice, these are right next door, but these are a couple elements away. So the farther they are away, and we know that oxygen is very electronegative, that means this one's going to be the most. So when we set up our list, we know that HC will be the lowest. That leaves the SP in the middle, and the OSI will be the highest. So when you're looking at bond polarity like this, it's just a matter of IDing which one is the most electronegative and which two are the farthest apart from each other. So expect to have a couple questions like this on the exam. Multiple choice, that type of problem, multi-select, etc., and you're good to go.